So this, I'd like to welcome Johannes Gooth from the Max Planck Institute of Chemical Physics of Solids in Dresden, in Germany. That's the advantage of Zoom, is we can really get top people like him to talk. He's the leader of the nanostructured quantum matter group there. Before going to Dresden, he got his diploma in 2011 from the University of Hamburg and the University of Lund in Sweden, and then a PhD from the University of Hamburg in 2014, and then went on to a postdoc at IBM Zurich. And after that, he visited Harvard and he worked with Amir Yacobi, and I guess we'll hear something about that today. He has done a variety of very interesting work. One that he won an award for, the Rudolf Kaiser Prize in 2020, is to look at the axial gravitational anomalies. Like, wow, so this is like cosmology, only it's done in a vial semi-metal niobium phosphate, and is published in 2017 in Nature. And so it shows how you can do really sort of high energy physics at low temperatures. Very interesting. Today he's going to talk to us about quantum Hall effect in 3D and what that means. So thanks very much for giving this presentation. Please go ahead.
Yeah, welcome everyone. Thanks, Bob, for the introduction. I thought since it's a seminar, I do it a bit of a lecture type style, and in the beginning, probably all of you, what I will tell in the beginning, you probably all of you have heard already, and but later on, it's going a bit more into the depth. I just want to have everyone on the same page. So let's start extremely simple, just with a 2D metal. Now this is the dispersion relation here of a two-dimensional metal without a magnetic field, and as soon as you apply a magnetic field, in the traditional view, it becomes an insulator with Landau levels, right? You get Landau quantization, and the system is really an insulator with Landau levels. If you enhance the magnetic fields, these gaps between the Landau levels get even bigger, and that is basically, or is the key message here. It's really an insulator, yeah? If you have a 2D system in a magnetic field, and instead of an energy momentum picture, as you can see here, you can also view this in only a momentum space picture, where each individual Landau level is represented by such a circle. And I'm introducing this here because we will need this later for a bit more deeper understanding of the 3D methods. Now, if you enhance your magnetic field, the gaps will get higher, and as you can see, what happens is that the radius of these rings in momentum space gets bigger, and they're pushed out of the Fermi level line or Fermi circle. That is this dashed line here. So this is the setup. Yeah. Now, from this kind of physics, which is the historical viewpoint, I would say, you would actually not expect to get any charge transport as long as your Fermi level is between two Landau levels. However, as you all know, in the 90s, Klaus von Klitzing discovered that you actually have charge transport still in 2D metals and strong magnetic fields when you have full Landau quantization, and actually a very special one, okay? So that is your Hall resistance becomes quantized as long as, exactly, and gets plateaus, no? With quantized values of h over 2e square to the square, and at these plateau values, and this is an important thing that I would like to point out here, is that the longitudinal resistance or resistivity goes to 0. And this you cannot understand actually in the historical viewpoint of this Landau level insulator. But very in the 90s also people noticed that what we're actually dealing with are not free electrons, but electron quasi-particles on a crystal lattice. And what this traditional view of an insulator and Landau quantization comes from is mainly from this part of the free electron part of the wave function, I would say. But there's also this kind of periodic term, which was so far neglected and was thought to play only a minor role. But apparently, it turns out to understand the quantum Hall effect, you desperately need to take this, part of the wave function into account. And I know that you all are very familiar with this, just to make sure that we are really on the same page, is that if you have a real object, you can define a Gaussian curvature, and due to the theorem of Gauss-Bonnet says that if you integrate the curvature across such a surface, right, then you get actually something like quantized numbers, only integers. And this theorem was known for a while, but later on it was discovered that this is actually essential to understand the quantum Hall effects in condensed matter physics. Because like for these real objects, you can also define something in momentum space for solids that is called the Berry curvature, right? It's a rather abstract thing. You can write it something like this. I'll go not into details up to now. But what is important is that you actually need to take into account this periodic function, or this function of the periodic lattice. And then if you look in this momentum states picture, then if you integrate this Berry curvature along a closed path in momentum space, it turns out for insulators, you get also there, like with the theorem of Gauss-Bonnet, only integer numbers. And if you have a trivial insulator, as we call it, yeah, then this integer number, which we call Chern number in this case, is 0. And if you have a non-trivial insulator, then you get a Chern number that is different from 0. And this is kind of the birth of topology, as you all know. And you can actually explain the quantum Hall effect from this. This is all reviewed actually in a paper of Jonathan. It's a PhD student of me, but it's of course was all known before this part. So how to understand now the quantum Hall effect of in this? So the inverse of the Hall resistance is the Hall conductivity, and it turns out that the Hall conductivity actually only measures, or simply measures, the Chern number of a quantum Hall system. So what you have to do is, now to get the Hall conductivity, you have to basically integrate all occupied Landau levels. So you have to sum over all occupied Landau levels, right? And the integral of the Berry curvature of them. So what you do is basically you integrate over the last Landau level, the second, and up to the Landau level that is occupied. This is this integral here, and then you just sum over the occupation of all occupied bands, and what you in the end get is something like 2e squared over h times the number of occupied Landau levels times the Chern number. And for typical gallium arsenide 2-dex, this Chern number is simply 1. So your Hall conductivity, or your inverse Hall resistance, gets basically 2e squared over h times n. So this is the setup. And I know that in principle, it's much more complex. You can have like a microscopic structure of edge channels and this kind of stuff and Hall systems. But I'd like to keep it with rather simple view today. Now, how does it look for the Hall curves? So let's say you have a system where you have 3 Landau levels occupied. It's this one. Yeah, then your Hall conductivity, then your Hall resistance is 1 over 2e squared over h times 3, because you have here, the total system it's a sum over 3 bands, and then you are at this point, and now you enhance the magnetic field. The Landau levels are pushed out of the circle, for example, to the lowest Landau level when only 1 Landau level is occupied here in the middle, and then you get a Hall conductivity of exactly 1 over e squared, 1 over e squared over h. Okay, so this is the setup. Still, this is still an insulator. So the question is, how actually can you how do you measure actually the electrons in this state? It turns out this is simply to an effect that is so-called the bulk boundary correspondence. and that says since the Berry curvature needs to be smooth in real space, if you put now a topological insulator, right, a non-trivial one like a quantum Hall system, next to a trivial one, which could be vacuum in this view is also a trivial insulator, then the Berry curvature has to be smooth in real space, and that means in this case that the bands here have to change. The band gap has to change sign, and it closes usually at the edge, and you get this metallic edge states which you can measure, and you get all the information about the bulk two-dimensional system in there. Okay, there's more to it. So people have thought, of course, not only about magnetic fields in 2D systems in magnetic field, but also about how can I use intrinsic parameters that in my Hamiltonian act or look like a magnetic field, like the magnetization or spin-orbit coupling. Can I create something similar? The answer is yes, of course. And you can, for example, get this anomalous quantum Hall effect in magnetic system, or simply a spin Hall effect in topological insulators. Okay, this is all 2D. Huh? This is all well established, well known. And now the question is, can actually the quantum Hall effect also occur in 3D methods? And the question might in the beginning, I mean, it's a very simple question in a sense, because the experiment putting a two-dimensional system simply in a magnetic field, measure the Hall resistance, cool it down, it's not a very complicated experiment. No? And you can ask, okay, what actually happens in 3D? No? We have a lot of 3D methods, so what happens? And what you usually read, and this is just an example, is, I highlighted this here, that in 3 dimension, the quantum Hall effect is forbidden because the 3rd dimension spreads Landau levels into overlapping bands, destroying the quantization. So this is a citation, and we will get closer, we will get a bit more into detail into what this actually means. But the essence of this is, in 3 dimensions, the quantum Hall effect does not exist. Huh? And the reason is, you can see this a bit here. Let's assume you have a 3D crystal, yeah, and you apply a magnetic field. What you then still get along KB. KB is here the direction of the magnetic field. The Landau levels actually disperse and remain still a matter. So you don't get a quantum. It seems you don't get a quantum Hall effect. So one of the first pioneering papers on how to circumvent on these problems and to actually introduce a quantum Hall effect in 3D methods comes actually from Harvard, from Bertrand Halperin. And his idea was the following. Let's assume we have a 3D method with a very small Fermi surface, okay? And then we apply a strong magnetic field, and a magnetic field that is actually strong enough to be in the lowest Landau level. Huh? Then at the Fermi position EF, at this, yeah, the distance between these points is of course 2kF. And now what can happen is that a density wave occurs, right? It could be a charge density wave or a charge density wave that nests these 2 points. And he said actually, okay, since this is effectively a 1D system, this is a very likely process. And what this would do is actually would electronically split such a 3D system in a stack of 2-dimensional layers, from each of which could host a quantum Hall system. This is the idea. No? And the measurement that, or the signature of this, what he proposed is, if you now measure the 3-dimensional Hall conductivity of your system, or the inverse, or take the inverse of the Hall resistivity, what you actually should measure is something like E²/h times the distance of this quantum Hall stacks, the periods of the stacks of quantum Hall layers. No? And you could also simply translate this into an argument, or translate this in a vector. So what he says is actually, okay, if we have such a system, right, then I can measure actually something that is related to the quantum Hall effect per layer that would appear in this 3-dimensional conductivity as E square over H times the vector, the lattice vector of this periodic modulation. So this was the idea. And now if you think, for example, about a charge density wave that nests exactly the Fermi surface, then you would actually get something, you would have to measure a Hall connectivity of E square over H times KFB. This is the Fermi wave vector along the magnetic field divided by pi. Okay, so far so good. And this was, I want to highlight this actually, already known 1987. Okay, this is a long time ago. Interestingly, approximately 2 years ago, this scaling that Bert van Hypering predicted was actually observed in the 3D Dirac metal zirconium pentatelluride. So this is data of Tang's work. The work was published in Nature in 2019, and there are now a few very interesting things. So they actually see, so the specialty of tungsten zirconium pentatelluride, zirconium pentatelluride, is that the Fermi surface is extremely small. Yeah? It's about 1% of the Brillouin zone. And you can actually reach the lowest Landau level with relatively moderate magnetic field. Here, about 1.3 Tesla in this sample. And as you can see, if you measure now the Hall conductivity, what you can see is that like in 2D systems, kind of plateauish feature emerge, right? And as soon as you cross the lowest Landau level, that's this peak here, then your Hall conductivity exhibits a plateau that scales precisely as Hypering predicted for this density wave induced quantum Hall, a stack of quantum Hall layers. No? And one interesting point is here that in this paper, they show one curve where actually also the Hall resistivity at low temperatures goes to zero. So these authors concluded it must be this charge density wave mechanism that we see here in zirconium pentatelluride, and this correlated or correlation-driven quantum Hall effect in a 3D system. The idea is, I mean, the system in this sense is not a real 3D system anymore, because you actually break it down into 2D layers, right? So it's saying that this is a 3D quantum Hall effect. It's a bit of a name issue, I think, to not confuse people. That's why I highlight this here. Okay, very good. And actually, not only that they found this in one sample, the scaling of the Hall effect, but they found this in many, and they could actually see that there's a linear correlation between this lambda q, this is simply the experimental height of these plateaus that they measure, and the actual Fermi wavelengths in their system. And the material was actually grown in US, in Brookhaven, at Brookhaven National Laboratory in New York. This is Genda Gooth. He's a grower. He grows these fantastic crystals. And every crystal that I'm talking about here in zirconium pentatelluride, whether it's from Tang or from us, is actually grown from Genda. This is very important. So all the samples where we did experiments on, which I will show now, are actually samples from Genda. Okay. So zirconium pentatelluride, very quickly, has an orthorhombic crystal structure. It looks like this. It's van der Waals, right? So they're just weakly bound, and their band structure consists of a single electron-like Fermi pocket at the Fermi energy. So it's really the simplest thing. It's a massive Dirac metal, right? That will be important later, but this is the only specialty in this. And this is kind of how a crystal looks. If I would now be a person in Harvard, I would actually let you touch these crystals. These are really like metallic samples. You can actually touch them, yeah? And hold them in your hand. These are metallic sticks. Now, why are they so certain that this is really a 3D metal? It's because what they did was they measured Shubnikov-de Haas oscillations as a function of angle. And I will not go into detail of this, but by doing this, you can actually follow and study the Fermi surface of this. And while it's a long ellipse, right, it's not an open Fermi surface. It really closes at a certain angle. And as you can see here in these two graphs, and really follows a nice 3-dimensional ellipse. So this is a really 3D system 3D metal that we're looking here into. Now, we actually at the same time, Tang and I got the crystals. My lab also got the crystals for a different reason, right? But when we heard about this experiment, we were actually extremely excited. I mean, if you have such a material system just lying around, and we wanted to study actually thermal transport in these, this is fantastic. But we had very soon a few questions that could not be solved, actually. And one of them is while here you can see that all of the samples, and we know, I think it's now in the world measured 40 plus samples, it's extremely well studied, that and all of them show these quasi or quantized Hall effect, these plateaus in the Hall effect that scale with the KF, with the Fermi wavelengths. Only one single sample at a single temperature, that was the one in the main paper, showed actually a vanishing longitudinal resistance like 2D systems. All other samples at all other temperatures show a finite resistance, and sometimes it's really high, as you can see here, no? This sample, and but the quantization remains, okay? The quantization remains. So this let us thought, okay, is this a bit strange, because if you would consider the Halperin mechanism and you would really have 2D quantum Hall systems stacked on top of each other, you would actually expect that for all of these samples, you would have non-dissipative S channels, and the resistance should go to 0. However, this seems not to be the case. So this vanishing resistance of actually this curve here, right, it was only observed at this very one sample at this only temperature. Yeah? So this already gave us a hint that this kind of vanishing resistance, longitudinal resistance in this one single sample, might not be directly correlated or connected to the observation of these Hall effects, this Hall plateaus and the scaling of this. And moreover, something that we found also a bit puzzling is that while, as I said, this one sample only showed a vanishing longitudinal resistivity at 0.6 Kelvin, right? The Hall effect in all other samples is actually observed up to 30 Kelvin or something like this. So the temperature scale is where you actually see the Hall plateaus with the precise and the exact scaling is actually 2 orders of magnitude higher. So this let us question, is there actually a charge density wave ongoing? And this is my postdoc Stan. He started this project and we said, okay, we have to investigate this. Yeah. And we started measuring. So we took exactly the same sample. This is one measurement of us. Huh? As you can see here, you can see the plateau here, the precise scaling. And we also see Shubnikov-de Haas oscillations in longitudinal resistivity, but they never go to 0. And none of the samples, down to 50 millikelvin. And so the first question that we asked us, okay, can we somehow probe the thermodynamics of the system? Because that's what you would do if you probe a phase transition to a charge density wave system. And the problem with heat capacity is that there are so few electrons that everything is dominated by the phonons. So we decided to go for to measure the Seebeck effect or the thermal power, which you can understand actually as entropy transported by particle across the temperature gradient. And so what you measure is basically you apply a temperature gradient to your sample and measure the voltage that builds up in magnetic field. And we did this. So these are the experiments. These are the magnetic fields along all crystallographic axes. Yeah? And but we in this experiment we found no signatures of any kind of phase transition. And what we actually saw were simple quantum oscillations in the thermal power. We analyzed them with Lifshitz-Kołowicz, and we got precisely the same results as we got from resistivity measurements. And everything that we saw so far in this thermodynamic property, if you want so, is that there is a simple Dirac Fermi surface. So there is no charge density wave instability, which you would see as a peak or something like this in the Seebeck effect. We went further on, since we are at Max Planck and Claudia Felser's group is next to us. She has a fantastic infrastructure, and we also studied magnetization, right? And to probe whether we see something like a charge density wave formation in another thermodynamic property that is not related to photons. And we did this. These are the experiments. I won't go into detail, but the essence is that as in the Seebeck effect, we only saw simple quantum oscillations in the magnetization on paramagnetic background, right? And again, these experiments are simply consistent with a single pocket. And since the paramagnetic background is so large, this indicates actually that you have a very small effective mass. But this was also consistent with previous ARPES measurement. It's a Dirac semi-metal, so the mass is actually naturally quite low. Then to study the electronic spectrum of zirconium pentatelluride in magnetic fields even further, we asked Stuart Parkin, who sits here next to us in Halle, also in Max Planck, to look at STM data and see whether he can actually see something like gap opening in magnetic fields in STM. And his people did a fantastic job in doing this, but down to 400 millikelvin in magnetic fields up to 5 Tesla, which is very deep in the quantum limit already. Remember, the quantum limit is at 1.3 Tesla. They found no signatures at all for charge density wave formation. They saw, so you cannot see this here very well in this little picture here. They saw Landau quantization, but they did not see any kind of signatures of formation of a charge density wave. And one important thing is here, what they observed is, and this is a specialty again of a Dirac semi-metal, that the band edge, so the lowest Landau level, did not move very much in magnetic fields. But that's all. No? And this was actually known before, but never, of course, done on these samples that show this whole plateaus and resistance. But we couldn't find a charge density wave either in this experiment. Then, as a next step, since charge density waves are usually induced either by electron-electron interaction, that is too weak that you can estimate here for zirconium pentatelluride. This was known, but one possibility was that you have a very strong electron-phonon interaction that induces, like in a Peierls mechanism, a charge density wave in magnetic fields. So what we did was we measured the ultrasound attenuation and the ultrasound velocity change in magnetic field in these samples. And what you can see is actually that the electrons and photons are slightly coupled. So you see basically the quantum oscillations of the electrons, so the Landau levels here, formation in the ultrasound, right? But with a very simple and standard model, it's like the Lifshitz-Kosevic model for ultrasound attenuation. We fitted this data, and it fits fairly well here, this middle region. And the electron-phonon coupling that we get from these fits is actually 2 orders of magnitude too low to induce a charge density wave. So that is actually estimated by theory to get a charge density wave. So also these experiments are consistent with a simple Fermi surface and no charge density wave emerging. Then what also happens if you get a charge density wave, then your lattice should be modulated. So we also looked at this. We looked in a synchrotron in XRD spectra in magnetic fields and looked whether you see some kind of anomaly occurring in the crystal lattice when you apply a magnetic field, but we found nothing. This is one example here in a curve. And we also studied Raman and see if because it's known that in Raman, if you have a charge density wave transition, you see additional peaks appearing. And these are Raman spectra for various fields at 2 Kelvin, but we saw nothing of this. It remained a simple, everything is consistent with a simple Fermi surface. Okay, now you could ask actually, okay, if there is no charge density wave, has the data that we and other people observed, especially Tanger, actually has it anything to do with quantum Hall physics, right? Or is it something completely different? And one thing that makes us experimentally very certain that it has something with quantum Hall physics is, and that it fulfills an empirical relation that was actually found only for 2D quantum Hall systems. And that is that the magnetic fields times the Hall conductivity, the derivative of the Hall conductivity with respect to the magnetic field is proportional to the longitudinal resistivity. The proportionality factor here is gamma, which measures kind of the electron electron density fluctuations in your system, and this is a particular relation for quantum Hall systems. And if you check this for the zirconium pentatelluride samples, actually this relation holds pretty well with a gamma factor that is well in the range for two-dimensional quantum Hall systems. Okay, so this experimental, this is an experimental hint that what we and especially Tang saw is actually related to quantum Hall physics, but the whole system does not undergo a phase transition. It simply remains a metal, a three-dimensional metal in a magnetic field. So we looked into this a bit deeper, and for theoreticians, it's probably very obvious what comes now. But for us experimentalists, we had to take a bit of time to look into this. So if you let's actually see what happens if you apply a magnetic field to a three-dimensional metal. And now here, since it's a four-dimensional problem, energy and the three momentum directions, I use this kind of plot. So kx is to the left, ky is to the right, sorry, and kx is to the right. And now if you apply a magnetic field, what happens is that actually within the kx ky plane, very similar to a 2D system, your system becomes an insulator, yeah, or like if you only consider this plane in case of momentum. However, your system remains dispersive in Z along the magnetic field. Okay, and so it remains a metal. So as I described before, so understanding this from a point of topology might be very different, right? Because these topological orders are only quantized if you have very special band structures like wire semimetals or something like this, or insulators in 2D. No? And exactly. So this is what happens if you enhance the magnetic field. And the Landau levels, they split apart, right? But the system remains always a metal. It's not going to be a topological insulator ever, right? Now the momentum space picture is like this. You actually, instead of only getting rings, you get now this kind of so-called Landau tubes. They look like this, and if you apply magnetic field, you do two things. So the height of these Landau tubes is going down, and at some point they will be rings and will be pushed out. Okay, so this is what's going to happen. And now I asked one of my students actually to look into the same formalism, how you derive in this very simplified way, how you derive quantum Hall physics from topology and Chern numbers to do this for these kind of 3D methods. And what you find is actually that you can describe the integral about the kx ky plane comes out to be very precisely what you would expect for a 2D system. This is this part here in front, right? No, this is basically integrating the Berry curvature along these kind of circles as we did as you do for the 2D quantum Hall effect. But now, since it's a 3D system and you look at the conductivities, you have to basically also integrate these circles then along the height of these tubes. No? This is what comes into here. And this is actually the part that destroys your quantization, right? If you would not have a tube here and no height, then you would get really like a 2D, only a quantized value for the conductivity. Now, this integral is actually pretty simple for most of the times. So you can express this simply as the height of this tube divided by 2 pi. And what you then do is you sum over, what you do is basically you have to sum for each individual band here. You have to sum over the tube height in addition to this 2D plane integration. Okay, that's what you do. And now a very special case, because it's actually very simple. There's only one height. That's why I'd like to discuss here is actually when you are in the quantum limit in the zeroth Landau level. And what happens then is that your Hall conductivity becomes here the E square over h times the height of this last tube, okay, divided by pi. And now in very general systems, this kind of height of the tubes will actually move with magnetic field. right? So that is probably why you for example, in parabolic systems like indium arsenide, you would actually not expect to see plateaus. However, one specialty about Dirac semi-methods is what we had actually seen before in the STM data, is that the lowest Landau level is independent of the magnetic field. So the Landau quantity, so it doesn't move in magnetic field if you apply this, right? And then what happens then in Dirac methods is essentially this, that your lowest Landau level remains, so the height of this thing remains for all peaks, for all fields at 2 kFz, so 2 times the Fermi wave vector, and it doesn't move through magnetic field. So if you're on the lowest Landau level, then you expect actually a plateau that scales with 2e squared over h times kfz divided by p. And this is exactly what was predicted by Halperin, but for a completely different reason. Okay, and this actually explains the data in zirconium pentatoroid very well. And if you would now just go back to this kind of model, if you have like 3 tubes in here, then this height is not very well defined because Landau level 3 and 2 still move with fields, so and the plateaus are not well pronounced. But as less and less and less Landau levels you get, you see here the plateaus evolving, and at some point you're on the lowest Landau level and reach this plateauish value. The Landau levels can still move a bit due to Siemens splitting. So this is probably why this is not completely smooth here on top. Yeah. But this is a relatively small effect. And importantly, and I really want to highlight this, the system remains all the time a metal. And that means that you do not have a non-dissipative transport. Your density of states at every point in the magnetic field is finite, and you get a finite, therefore also a finite resistivity, despite descaling of the quantum Hall effect, of the Hall effect, sorry, not quantum. And exactly, so people nowadays call it quasi-quantized Hall effect. I'm not sure if this is a better name. It's certainly not quantized, yeah. But this is what you get for a Dirac method. Now, as a cross-check, we ask a collaborator of us, Tobias Meng from TU Dresden, to check also the other transport parameters. Just take this very simple Dirac model system and calculate the magnetization, the Seebeck, the Nernst, and so on, using Kubo, but not with any charge density wave transition, just with a spherical Dirac, an ellipse Dirac Fermi surface, and put our experimental parameters in. And the theory and the experiment agrees quite well. The only thing that does not agree quite well is here at low fields, the longitudinal resistivity. And this is due to the fact that in the theory, we kept one scattering time for Landau level broadening and for transport, which it's not a valid assumption actually, but we wanted to keep it simple, and the theory reproduces the experiments quite on a quite decent level, although it's so simple. Okay. Now, the same effect can actually be seen in hafnium pentatoroid. It's like of the little sister of zirconium pentatoroid. And just for fun, we bought a very pure indium arsenide wafer that was optimized for semiconductor industry. These wafers are 3-dimensional crystals, which have mobilities up to 1 million. Nowadays, and we just checked if we would see the same effect in indium arsenide, and it's less pronounced because the height of the Landau tube, also in the lowest in the quantum limit, always moves with magnetic field. That's why there's a slope on here, but it fulfills the predictions for these 3-dimensional methods in magnetic fields quite well, considering this Berry curvature mechanism. And there's more to it. So we can actually now describe also old indium antimonade data, antimonade data, and YC methods, and so on. This can be all understood in this framework. Okay. Now there, as a last point, I'd like to mention something that we found out also quite interesting. Now we could of course ask, okay, if you have the similarities to an integer quantum Hall effect, do you also see like something like correlated states in these 3D systems, like so in correspondence to a fractional quantum Hall effect in 2D systems? And it turns out that in zirconium pentatelluride, the answer is down to 50 millikelvin. The answer is no. So even at small fields, this is here. So this is the lowest lambda level. You see a bit of spin splitting here, but nothing special. And also in the quantum limit at very high magnetic fields, it's the Hall conductivity is just smooth. And this movement here is due to the Siemens splitting in these systems. Okay. However, hafnium pentatelluride has a bigger spin-orbit coupling, and if you're familiar with the fractional quantum Hall effect, then you might know that actually strong spin-orbit coupling stabilizes fractional quantum Hall states. Yeah? So we took also hafnium pentatelluride, cooled it down, and found something very interesting. So at low fields, it looks very similar to zirconium pentatelluride. However, in high magnetic field, in the ultra quantum limit, where you would expect nothing to happen anymore in a simple one-dimensional, in a simple metal, we've suddenly found in all samples investigated an additional plateau which height corresponds to 3/5. 3/5 is a bit taken with care. We discussed about filling factors, but it's not clear what actually a filling factor means in a 3D system. Yeah. So what we can say experimentally, that in all the samples that we have, the height of this is around 3/5 compared to the plateau of the lowest nano level. And what you also see is an additional peak here in the longitudinal resistivity, like for the Landau levels, which also scales with 3/5 to the position here. To the onset of the quantum limit. Oh, sorry, and we also checked the derivative relations for this, if it's really quantum Hall physics, or if we can get a hint that it's actually quantum Hall physics. The answer is yes. So this is the plot that you can see here, and we also, in addition, we checked the energy scales, and the energy scales for these plateaus here, or for this little plateau thing here, and this feature here, is about an order of magnitude lower in energy and diminishes at much lower temperatures than these pronounced plateaus here or here that correspond to the ultra quantum limit of the simple Fermi surface. So as a message to take with you today, or the message of this talk should really be that the Hall conductivity in 3D metals is actually related to the quantum Hall effect in 3D electron systems, but must be always scaled by a characteristic length scale that I name here pi over delta kz, and this can in general depend on B, on magnetic field, huh? And in particular in the quantum limit, you always get a formula that looks very similar to the formula that Halperin came up with. And if you think about this, if you want to generalize the idea of Halperin a bit more, then you could say, okay, you can either you can break your system down into 2 decks by introducing a length scale that is really a spatial length scale, right? Or the system is broken down somehow, or cut in the third direction by something different, by a length scale that is simply set by the band structure. And exactly. So, and with this, I'd like to, I'm happy to answer to questions, and hope you could take something from it. Thanks.
Gee, thanks very much. That's really interesting. I've thought about these things before, but not found these kind of interesting things you've got. I guess as a first question, if people want to ask questions, please type something into chat. and then we'll read it. The way that things work, you can't directly raise your hands, and because with this many people. But a question is, what if I were to make a new material that would have the same kind of behavior? What would you recommend in general, sort of simple characteristics, or what would be the goal of making some analog of hafnium telluride 5 or
Yeah, so to really see this precisely, I mean, the question is, yeah, exactly. To see this experimentally precisely, what you would like to have is something that doesn't move in magnetic field to really get a plateau, right? So
right.
wire semi-methods are a good thing, Dirac semi-methods, nodal line semi-methods. And other than that, the discussion is actually very similar to the discussion of the two-dimensional Hall effect. When do you observe this? So one thing that is very important here, all the calculations that have been done and considerations only work if your Fermi level is fixed. Yeah? And that means if you apply magnetic field, that your charge carrier concentration of the free particles actually has to vary to balance it. And in 2D systems, that is, if you have enough defects that can compensate a bit, this is easy. However, in normal 3D methods, you have a lot of carriers, for example, in copper, right? And there is no way that this can happen, right? So what you would like to look into is very small Fermi surfaces where the absolute change of free carriers with magnetic field is so small that it can actually be compensated by defect states or something like this. Right?
I see.
To have this prediction. We, for example, looked into mercury selenide, extremely clean crystals. We also reached the quantum limit, but that the Fermi level is a bit higher. So the quantum level is reached, the quantum limit is reached at around 20 Tesla. And it's just a line. It's really just a line, like Drude, like in a Drude formula. You don't see anything. And the reason is because the metal is the crystal is so clean, that the Fermi level that the Fermi level moves all the time.
I said dirt is good in something.
Thanks.
I have a comment from Philip Kim. Says similar phenomena have been observed in graphite and possibly in bismuth, which is a semi-metal with strong Fermi, which is a semi-metal with strong Fermi surface anisotropy. Then a question from Yashang Wang. It says, can you elaborate on the comparison between zirconium telluride 5 and indium arsenide ? Does it come from the Fermi surface of indium arsenide is less elongated?
That is actually exactly, yeah, that is actually a good question. That's actually a good question. That's something we don't know, because at the moment we haven't found a Dirac semi-metal, a three-dimensional one, that has, for example, a cubic crystal. So the only thing that we compare at the moment is like a parabolic cubic metal, with a parabolic band structure that's indium arsenide to this very elongated zirconium pentatelluride. So actually, we have not sorted out these facts. But my intuition is that it's rather about, to see this effect, it's rather about the last Landau level not moving in fields to really see this plateauish thing.
I see. Okay, we have a question from Bert Halprin. It says, if one could neglect impurities, then the Hall conductance would depend only on the density of electrons. In other words, KFC varies inversely as magnetic field and the large field limit. So if there is a plateau, it means that KFC is pinned. So you must have some source for electrons at localized states to feed it. What do you think?
Yeah, absolutely. I fully agree. Exactly. And that is actually the reason why this probably works only compared to 2D systems for very tiny Fermi surfaces. Because I mean, so what we believe at the moment, what happens with the competitor is that it's compensated by defect states simply, right? Is this do I understand the question correct?
Sure, I think that's it, to feed the density.
Yeah.
Okay, any other questions? Please type quickly. in chat? I'm counting now. I'll give it a minute. Okay. Let's see, another one. It says, from Bird again, it says in the original paper on this, it was claimed that the charge density wave spacing gets pinned at some commensurate multiple of the lattice period.
Yes.
Yeah.
Mhm.
Okay.
Exactly. Exactly.
Okay. Well, great. Well, thank you so much. And a very interesting business to understand how this. Oh, wait a minute. One last question from Bert. What pins kilohertz? I'm not sure what I mean in your case. Oh, the KFC in your case. What pins the Fermi wave vector in the keys?
Yeah. So
Z
this
Rex
is
in your
this.
case.
Yeah. This is simply the nature of the Dirac dispersion in magnetic fields. So the lowest Landau level never moves. If you consider Landau quantization, it's simply it's independent. So the position of it's independent of magnetic field. All others are moved up, right?
Okay.
Like in parabolic bands, but the last one is pinned, and that is why we see why you probably see this.
Okay.
See this plateau.
Okay. Great. Well, whoops. Bert says we should talk. So
I'm very happy. I'm very
give
happy
him
to do that.
a link and you can figure it out.
Yeah.
Well, great. Well,
That's why
thank you. Thank you so much. And, tip back a beer or whatever for my sake. And I'll keep working here. But thank you so much for, thank you so much for wiring up with this across the ocean.
It was a pleasure. Many thanks.
Great.
Thank you so much. Bye.
Ciao.